So I'm very happy to present this work that has been carried out with my colleagues from the Zhou laboratory in France. The context of the work is about the development of the new eddy current non-destructive evaluation techniques, which aim at providing integrity diagnosis of industrial structures, in the goal to prevent accidents during operations, and also to optimize lifetime and maintenance procedures. Eddy current techniques only apply to electrically conducting structures and finds many applications in the nuclear and aviation industries and tends to spread to other industrial sectors. These techniques are very popular because they are non-contact, easy to use, very cheap, sensitive to various kinds of defects, such as holes, cracks, and so on, and they are also non-polluting. For this reason, the development of more accurate, more reliable, and more rapid eddy current techniques are still nowadays an industrial need and a challenge, although it has been used for many decades now. The basic principle of the eddy current techniques lies in an electromagnetic coupling between an inducer and a structure on the test, which is called here a target. And resulting from this coupling, there is the inducing of eddy currents within the target and the apparition of a magnetic field distribution at the surface of the target. This distribution may be sensed by adequate magnetic sensor, and the so-called provided eddy current data are then depending on the target geometry and on the electromagnetic properties of this target. As you may know, when you excite with a plain magnetic wave conducting material, then the intensity of the induced current will obey to a exponential decreasing law, known as the skin effect, which means that you will not be able to evaluate the material as deep as you wish because of this skin effect. Added to other limitations and drawbacks, in fact, generally speaking, the technique is quite difficult to elaborate a quantitative evaluation of the parameters of the target starting from the available eddy current data. In other words, the eddy current non-destructive evaluation techniques are known as an ill-posed problem, and one step could be to try to bypass these limitations. The first step would be to try to develop new techniques or new devices able to extend the informative content of the data given by the device. So, to this end, we have proposed a new device, which is called a pulsed eddy current magneto-optic imaging device. This device is based on the following principle. First of all, it is able to induce pulsed eddy current in the structure on the test, and these currents are also of adjustable orientation. As you can see on this picture, when a defect is present in the structure, then the eddy current flow will be modified, resulting in the apparition of new magnetic component, which has to be imaged in the vicinity of the defect. It can be imaged here. We choose to image it thanks to a magneto-optic transducer, which is able, when it is enlightened with polarized light, to convert actually the amplitude of the magnetic field into a variation of light intensity, which may be recorded by a CCD camera. This is made through a Faraday effect occurring in the magneto-optic material. Here you have some pictures of the actual device that was built, and you have some of the main features of the device which are gathered here. You can see in particular that the spatial resolution that we obtain is about 100 micron by 100 micron in a 65 diameter circular image. Now, the problem is not as simple as that when you try to record an image, because it's not only an image that you want to record, but a sequence of images which are the two-dimensional time response to an eddy current impulse within the material. So this is done thanks to a stroboscopic approach in which eddy current impulses are repeatedly induced in the material, and the magnetic field cartography is then repeatedly acquired by the camera. This is done by the means of light flashes which are synchronized with the eddy current pulses, and progressively time shifted during all the period of the eddy current pulses. in this manner, you are able to build the whole sequence of the two-dimensional response of the system to an eddy current impulse. Now let's see how it works on an example of a structure which has to be imaged. The structure is composed of three aluminum plate layers featuring a defect on the upper plate. Now you can see here the two-dimensional time response. Well, you will shortly see it. No, you won't. Okay. So this is the sequence of the image that we obtain in the time response, and you can see, thanks to a very simple spatial analysis, that, for example, a spatial feature can be determined here. The spatial feature is the distance between the two peaks that appears at the end of the defect. These peaks, in fact, represent the magnetic field distribution that appears because of the defect. And you can see that this distance between the peaks is highly correlated to the actual length of the defect. For example, for defects ranging from 4 mm in length to 8 mm. Now let's look at another configuration in which this time the defect is placed in the second plate. Then you get, no, doesn't work, too bad. You get another time response of the system, in which you could see, if it worked, that actually the magnetic patterns appeared, but delayed by comparison to the first one, because there is more time needed for the magnetic field to reach the buried defect. So another analysis, time analysis, may be carried out, in which you could see that the time of apparition of the more intense pixel of the image will be strongly dependent on the position of the defect within the structure. Here for the position in the first plate, the second plate, or the third plate. Now we can generalize this analysis to various kinds of defects. For example, these 4 surface breaking defects here. And I only take the impulse response relatively to 1 pixel of the image. And you obtain for these 4 defects these 4 responses, which are perfectly synchronized, only the amplitude varies accordingly to the height of the defect. Now, if we consider buried defects of the same size, but they are buried within the first plate, you have different impulse response. They are desynchronized. And if for a clearer image, I only take the maximum value of the response that we obtain, and I put it in this representation plane, in which you have pixel intensity versus time. You can see that for open cracks, surface crack, and buried crack, you get different points, starting from these features. And if we complete the analysis with other buried defects, you can see here again that we obtain different position in this representation plane. For example, the most buried defect, the deeper defect, number 9, appears very lately with a small amplitude because it is so buried in the structure. Now, we could also consider to extract a time-space feature from this sequence of images instead of only time or only spatial. And for example, you can try to evaluate the diameter of the magnetic pattern that appears due to the defect. This diameter, called delta x here, you can follow the evolution during time, and you can see that for the surface defect, you obtain these red evolution of this diameter with a synchronized rising time and a desynchronized falling time, and various amplitudes that are reached. Now for a buried defect, you can see that it's completely another story. You have delayed rising time, delayed falling time, and also you can see that all the amplitudes are the same, which translates the fact that the defects are reaching the same depth within the material. Now the last experiment I would like to show is the following. It is in fact a more complex situation in which you have a rivet in a riveted assembly, and a crack which is in a second plate. So it is too bad that the movie doesn't work. Okay. Okay, the sequence of image is the following. You can see that at first, in the beginning of the sequence, you have patterns which are only due to the head of the rivet, and then later on, when the field has time to propagate within the depth of the material, you can see new patterns. Here are blue patterns, which is due to the buried crack. So, as a conclusion, I would say that space and time analysis of this type of assembly is very rich, very relevant to try to dissociate various kind of defects or elements in the structure. As a conclusion, I would say that we have built a proof of concept for a pulse eddy current imaging device. We have pointed out the advantages that can be obtained to try to extract time and space features from these images, and further work could aim at evaluating the location, the length, the depth, and the volume of various defects starting from these features. Also, other potential applications may be carried out. For example, the monitoring of the magnetic field which radiates from aging power electronic devices. Thank you for your attention.